For this next section, 8.7, we're going to talk about numerical integration. Sometimes it is just not possible to find some sort of a workable antiderivative for a function, so we can approximate the area under a curve. And one method is using trapezoids. So if you look at the picture that I have here on the screen, you have this function, y equals f of x, represented by this blue curve, and a series of trapezoids are used to estimate its area. So the x-axis is subdivided into these intervals of width delta x, and if you remember the way to find the area of a trapezoid, you're going to take that width delta x times the average of the two heights, in this case the left and the right height, represented by y1 and y2. So if we use that idea and find the area of all of these different trapezoids and then sum them up, we can approximate the area under the curve. And that is summarized for us in the trapezoidal rule. So it says, to approximate the area under the curve f of x from a to b, we can use this rule. So it's going to be delta x over 2, and then it's y naught plus 2y1 plus 2y2, and so on, down to that last y value, yn. So you'll see here that except for the first and the last y value, the rest of them are going to be doubled. The reason for that, in case you're wondering, is let's say I'm looking at this leftmost trapezoid. So I'm going to use this first height, y naught, and then I'll also use this one, y1. Well, on that second trapezoid, I'm going to use y1 again. So it's used twice, hence it's twice in the formula. The only ones that are not used twice are the very left y value and the very right y value, hence they're only once in the formula. So we're going to take this formula and look at an example. So we have here a rectangular swimming pool is 30 feet wide and 50 feet long. This table shows the depth h of x of the water at 5-foot intervals from one end of the pool to the other. Estimate the volume of the water in the pool using the trapezoidal rule with n equals 10 applied to the integral. The volume is the integral from 0 to 50 of 30 times h of x dx. So we got a lot going on here. What we're going to do is we're going to use the trapezoidal rule to integrate that h of x dx from 0 to 50, and then we're going to need to make sure to multiply it by 30, which is the width of the pool, to find the volume, okay? So basically we're integrating along the length, so there's 0 to 50, and then the function here is the depth of the pool, okay? So there's our 3 dimensions. Here's the width, this is the length, this is the depth. So I'm going to use that trapezoidal rule. We have, in that rule, it needs a delta x. There we go. And to find delta x, we take the position at the far end, so that's 50, minus the starting position, 0, and divide that by the number of subintervals, 10. So we get 50 over 10, so delta x is going to be 5. That delta x represents our d of x. So using the trapezoidal rule, we get t equals delta x over 2, so that's going to be 5 over 2. Then remember, the initial y value and the final y value are going to be by themselves. Every other y value will be doubled. So you'd have 6.0 plus 2 times 8.2 plus 2 times 9.1, and we'll just continue for all of those y values. Almost done here. Okay. And then remember that last one does not get doubled. There we go. So it's not a hard process, just a little tedious to write this out. If you go ahead and do all the arithmetic inside those brackets, you're going to get a grand total of 213.2. So that leaves us with 5 halves times 213.2. And when you multiply that out, it works out to be 533. Now, if you remember correctly, to find the volume, it's not just 533. The volume is going to be 30 times that 533, because we could rewrite this as a 30 in front of that integral. Okay, so the 533 is this part. Now we're going to multiply by 30 to get the volume. So the volume here is 15,990 cubic feet.